one of the topics we have left over already is single phase induction motor. This is one of the motors which is extensively used in household applications. If you look at any household, normally at least a dozen single phase induction motors or single phase motors are used in any household. So, for example, if you look at mixer, grinder, we use a single phase series motor which is actually known as universal motor. Then all the fans that we use, right, they are all single phase induction motor. If we look at actually hair dryer or some of the shavers and so on, hand drills, many of them, hand drills generally is universal motor, whereas these are all generally single phase induction motor. Lawn mowers, if you look at rest of pumping, water pumping motor, those are all single phase induction motor. So, this is a very competitive market. Generally, if you look at the normal market price, because even if you increase the efficiency tremendously, but if the price increases even slightly, nobody will be willing to buy this kind of single phase induction motor. So, it is really a competitive market in that sense. Now, let us try to look at how the single phase induction motor works. So, we are going to look at the topics as follows. First, we will look at construction, then we will look at the operating principle based on double revolving field theory. Okay. We had seen already the revolving field theory when we were discussing 3-phase induction motor. This is a double revolving field theory. Then we will look at the equivalent circuit. Then we will be looking at expressions for torque, power, etc. After this, we will be looking at OC and SC test, how to determine the parameters of the machine. Finally, we will look at some starting methods. So, we are just looking at the glimpse of single phase induction motor, nothing more than that. So, these are the topics that are going to be covered during this lecture. As far as the construction is concerned, normally the winding we have in the stator is a single phase distributed winding. So, I am probably going to have, if it is a 2-pole construction, I am going to have the winding distributed all over the slots like this. Okay. So, this side let us say is carrying dot current and this side is going to carry cross current. Okay. Now, I am showing a 2-pole construction. Now, because it is dot current and cross current, I am going to have the stator flux rather looking at it in this direction. I have the rotor here. The rotor is very similar to the squirrel cage rotor of the 3-phase motor. So, I am going to have the squirrel cage bar arranged around the outer periphery of the rotor, and it is going to be short circuited the same way I may have basically the short circuiting end rings which are actually sitting here. So, these are all generally made up of aluminum. Hardly ever we use copper in single phase induction motor because copper is more costly. So, normally we use aluminum. And this can work very well whether it is 3-phase, 2-phase, single phase, 4-pole, 2-pole, 8-pole, anything it can work very well, not a problem at all. So, we are going to have this construction, the cross sectional view I have shown here. Now, very clearly because it is a pulsating MMF, what I mean by pulsating MMF is, if I say this is theta equal to 0, clearly this is theta equal to 180 degrees. So, if I actually draw I am going to have actually the MMF looking somewhat like this. This is how it is going to be. So, let us say this is theta equal to 0, this is theta equal to 90 and this is going to be theta equal to 270 degrees and this is 360 degrees. So, this is what we have drawn. So, this is the kind of MMF or flux we are going to look at a particular omega t, Okay. Now, if I look at another omega t, the current might have decreased in magnitude. When it decreases in magnitude, I am going to have the same flux, but looking like this. And I will have further reduction in the flux as time goes by, right, because it is a sinusoidal current. Please remember, it is a single phase current. At some point, it will become completely 0. After some time, the current will start reversing. So, we may see something like this as the flux. Then it will become higher, right. So, I hope you get my point. Basically, the flux magnitude is going to change. So, flux magnitude is changing, but it is stationary flux. This is a stationary flux. It is not rotating basically. So, it is stationary flux. Now, as far as the rotor is concerned, the rotor is seeing this pulsating MMF, because of which this will also have induced. And that induced flux will be opposing whatever is the original flux. So, we will have the rotor flux in the opposite direction. But if you look at the angle between these two, it is 180 degrees. So, if I try to look at what is the torque produced is generally proportional to the cross product of phi s and phi r. And that means sine of angle between them will come into picture. So, that will be 0 when I look at the starting of the machine. So, I will not be able to get any starting torque in a single phase induction motor as such if I do not make any arrangement for starting. That is because I have a pulsating flux in the stator, I have a corresponding pulsating flux in the rotor which is exactly opposite. So, the angle between them will be only 180 degrees. So, I will not be able to really get any torque. Okay. So much so as far as the construction of this particular single phase induction motor is concerned. One major point I want you to notice is there is no difference between the cage rotor construction of single phase motor and 3-phase motor. Okay. Now, if I actually look at this pulse, the MMF or flux, I said that it is probably going to have a magnitude like this, then it is going to decrease, decrease and decrease further and it will become 0, then it will start increasing in the opposite direction. This is what I said with respect to time. If I look at time, this is how it is going to change. Okay. If this is the way it is going to be, I can imagine it somewhat like this. If this total magnitude is some phi m, I can imagine that there are 2 phi m by 2 fluxes available with me. Okay. And one is rotating in say clockwise direction, the other one is rotating in anti-clockwise direction. When both are at stationary position currently, the resultant of this will be double this value, something like this. This is going to be phi m at let us say t equal to 0 or omega t equal to 0. If I look at what happens at omega t equal to 30, I am going to have this displaced by 30 degrees and this also displaced by 30 degrees because it is rotating in opposite direction. This is 30 degrees and this is also 30 degrees. So, what I am going to get is this is phi m by 2 and this is also phi m by 2. So, I am going to get phi m by 2 cos 30 and phi m by 2 cos 30, both of them added together, the resultant will be along this. This is how it is going to be. So, the resultant will be only this much. This is going to be the resultant, right. So, at 30 degrees what I am going to get is 2 phi m by 2 multiplied by cos of 30. So, this is going to be 0.866 times phi m, right. Now, if I try to look at, this is at omega t equal to 30. If I look at omega t equal to 60 degrees, I can similarly write, I am going to have this as the mid position. I am going to have this side actually having 60 degree displacement, this side also having 60 degree displacement, right. So, the resultant, if I try to look at it, I am going to get something like this. So, the resultant will be along this like this. So, this will be 2 phi m by 2 cos of 60, which will be phi m by 2 itself, right. So, I am going to get phi m by 2, right. I am going to get phi m by 2. Now, if I look at 90, please note both these things are exactly opposing each other. This is at omega t equal to 90. So, the resultant will be 0. So, what we talked about is coming true if I try to look at the fluxes, two of them each magnitude having phi m by 2 rotating in opposite senses, one in clockwise, one in anti-clockwise. You can also see that when phi becomes 180, both of them will be actually looking down. Both of them will be phi m by 2 like this, right. This is actually at omega t equal to 180 degrees. So, the resultant will be phi m itself along negative direction, right. So, that is corresponding to this particular period. So, you can very well see that if I consider two revolving magnetic fields, each having a magnitude of half the original magnitude of the magnetic field, the peak of the magnetic field, then it will be equivalent to a single phase pulsating field. So, when we analyze the single phase induction motor, we will analyze it as though we take two revolving magnetic field each of phi m by 2 magnitude. And we are going to consider this as though we have connected two 3-phase induction motors each having phi m by 2 magnitude in the opposite direction and how the rotor will react to that. So, you can imagine if I look at the induction motor characteristics, 3-phase induction motor characteristics, normally we draw it like this, right. So, this is let us say corresponding to ABC phase sequence or forward rotating magnetic field, clockwise or anti-clockwise. And we are going to take the other one again starting from the other omega s, but it is going to actually go like this, which is reverse rotating magnetic field. This is ACB sequence or this is reverse rotating magnetic field, right. Now, if I look at, this is actually the speed axis and this is the torque axis. So, if I look at speed equal to 0 point, I am going to have both these torque exactly being equal to each other. If I may call this as TF and if I may call this as TB, forward torque and reverse torque or backward torque, TF will be equal to TB at omega equal to 0. So, I will not have any net starting torque, because of which I will not have this machine. So, single phase induction motor is inherently not self-starting. It will not be able to start on its own. This is what you would have seen many times in railway compartments and all. Many fans will not start running, but if you give it a push in one direction, it will start running. That means, if you give an initial torque, then it will be able to run. That is because if I look at the resultant of these two torques, after all the single phase induction motor is having both these fields. This is forward and this is reverse, both are existing. So, the net torque will be the resultant of these two. So, if I draw the resultant, I have to subtract from forward the reverse and I can draw it somewhat like this. I am going to essentially get some torque somewhat like this, right. So, this is how the torque is going to be. So, this is going to be the resultant torque. So, you can see the moment I give a rotation either in forward direction or reverse direction, I do have some amount of torque available, because of which the motor will be able to pick up speed. Normally, most of the single phase induction motors will be less than 1 kilowatt rating. Very standard ratings are 0.25 HP, 0.5 HP, 1 HP and so on. Many of them are really small motors. So, the conductors will be really thin. So, which means resistance will be high. That means the copper losses are going to be high, which means efficiency will be low. Most of the single phase induction motors will have less than 50% efficiency. Nobody cares too much about the efficiency of the single phase induction motor, because if you want to improve the efficiency by making a better design, even if the cost increases slightly, nobody is going to buy your motor. It is a very competitive market. That is what I said. So, when we actually analyze the motor, it is exactly similar to induction motor, I said. So, in induction motor normally we have R1, X1, we will have very clearly Xm, we will have normally RC also, but most of the times we are going to neglect RC in the case of single phase induction motor for the sake of simplicity, and also because the resistance value that is connected in the stator is generally high, thin wires, that is the reason. Now, as far as rotor is concerned, the rotor has to be divided into two portions, one corresponding to forward, the other corresponding to reverse rotating magnetic field. So, if I say R2 and X2 are normally the rotor resistance and reactance, or referred to the stator side, it is R2 dash and X2 dash. For forward, let me take R2 dash by 2 and X2 dash by 2. Similarly, for reverse also, let me take half of it, R2 dash by 2, X2 dash by 2, because both are equally influenced by forward and reverse rotating magnetic fields. Now, if my machine is rotating in this direction, let us say it is rotating in this direction in omega r. If I am looking at forward revolving magnetic field, it may be rotating at omega s. This is corresponding to ABC phase sequence. If I am looking at reverse rotating magnetic field, it will be minus omega s, which is corresponding to ACB phase sequence. So, if I try to calculate the slip corresponding to forward rotating field, I should write omega s minus omega r divided by omega s, which is very similar to the normal flux of the induction motor, which is SF itself. Let me call this as S for simplicity. If I try to calculate what is SB, which is corresponding to reverse rotating magnetic field, that will be minus omega s minus omega r divided by minus omega s, which is very similar to the plugging operation. So, this can be written as 2 minus s, right. So, I am going to have two different slips corresponding to each of them. If you may recall what we wrote earlier in 3-phase induction motor, we used to write R2 dash by S. Here we have to write R2 dash by 2s, and here we have to write R2 dash by 2 into 2 minus s. Now, I am going to divide Xm also into two portions. This is corresponding to forward flux and this is corresponding to reverse flux. whatever I am drawing as the rotor parameter, again I am going to draw corresponding to forward side and backward side, right. I can very well draw this also as R1 and X1, otherwise I can write this as R1 by 2, X1 by 2. Similarly, here also I can draw this as R1 by 2 and X1 by 2, right. So, I should be able to draw it like this. Okay. Let me write here, this is R2 dash by 2s, this is X2 dash by 2, which means this voltage is going to be corresponding to EF or forward revolving magnetic field dependent induced EMF. Similarly, this is going to be EB, which is the reverse magnetic revolving magnetic field induced EMF. Okay. Now, this will be R2 dash by 2 multiplied by 2 minus S. Now, this is going to be X2 dash by 2. This is essentially the overall equivalent circuit of the single phase induction motor with the voltage V1 being applied here. We have derived this essentially from forward and reverse rotating magnetic field along with 3-phase induction motor equivalent circuit. Okay. Now, let us see how to get the power expressions. Now, I can look at this entire impedance whatever I am getting here as the forward side impedance. Similarly, whatever impedance I am getting here as the reverse side impedance. So, I can say ZF equal to, let us say, RF plus JXF, which will be equal to, please note XM by 2 is in parallel with R2 dash by 2S and X2 dash by 2. So, I can simply write this as JXM by 2 multiplied by R2 dash by 2S plus X2 dash by 2 divided by, because it is parallel combination, R2 dash by 2S plus J multiplied by X2 dash plus Xm by 2. Is that clear? So, this is going to be my ZF. So, similarly, I should be able to write what is ZB. ZB will be RB plus J times XB. That will be JXM by 2 multiplied by R2 dash by 2 multiplied by 2 minus S plus JX2 dash by 2. I am talking about this whole thing within one bracket, okay, divided by R2 dash by 2 multiplied by 2 minus S plus J multiplied by X2 dash plus Xm by 2. Okay. Now, if I say that the motor is drawing a current of some I1, the same current flows everywhere. So, I should be able to say I1 square RF will be the power that is taken by the rotor corresponding to forward revolving magnetic field. Similarly, PGB, which is actually the reverse rotating or backward rotating magnetic field input power, that will be I1 square multiplied by RB, right. This is going to be I1 square multiplied by RB. Now, PGF minus PGB is actually what is available as the power through the air gap or power which is available in the air gap. So, air gap power I can call it like this. Now, PGF minus PGB multiplied by 1 minus S will be the mechanical power that is available. Right. Now, I can talk about this PGF minus PGB divided by omega s as actually the torque that is available. Okay. Now, very clearly this is going to be a braking torque, whereas this is going to be the motoring torque. So, single phase induction motor will always have braking torque along with motoring torque. I can't help it, it will be always there, because of which I am not going to have really a good efficiency in this motor. So, 3-phase motor efficiency which has only forward torque, no braking torque at all. So, the 3-phase motor efficiency is always going to be greater than single phase motor efficiency as a rule. And one more thing I should be able to say is, after all, in the case of single phase motor, we are looking at actually voltage somewhat like this. This is the applied voltage, right. The current is going to be probably lagging behind by certain angle. So, if I try to multiply V and I am definitely going to get some negative power here, I am going to get positive power here, again negative power here, positive power here and negative power here. This will be the power, right. So, if this is the power is oscillating, it is not a constant power. Now, if I look at the speed, because it is having mechanical time constant, speed is almost like a constant. Within this 20 millisecond period, if I try to look at it, speed will be almost like a constant, right. So, if I try to get what is the torque, right, that is essentially power divided by omega, right. So, that will definitely have oscillation. So, if you look at the torque will have some positive component, negative component like this. This is how the torque is going to be. The torque is not a constant torque, because of which there will be huge vibrations in the shaft. So, normally we will never tolerate such vibrations in bigger power capacity motors. So, single phase induction motors are never used for higher capacity applications, because first of all the efficiency is very low, it is not self starting, and also because I am going to have vibrations continuously in the shaft, which is definitely not tolerated in higher capacity applications, right. Now, let us try to take a look at how to determine the parameters of the single phase induction motor. We had already done for 3-phase induction motor this in detail. So, hopefully, we should be able to do it quite fast. Let us say I have basically under the no load condition, somehow I have started the motor. I have still not talked about starting methods. I have started the motor. After starting the motor, I am just running it on no load. I am trying to measure V naught, I naught and W naught. Let me show the circuit diagram also. I am going to have a single phase supply, which is actually 230 volts, 50 hertz, single phase supply. Okay. This is the variac I am going to have. From the variac, I am going to feed it to the single phase induction motor. The single phase induction motor normally is shown somewhat like this. There is a main winding. I am going to show this as M and MM simply. I definitely have to connect a voltmeter and ammeter, which I have not shown right now. So, I have to show an ammeter and I can connect a voltmeter right across this. Of course, I have to have a wattmeter also. So, this wattmeter I am showing it somewhat like this. So, wattmeter is here, this is the pressure coil, this is the current coil. Okay. Now, I have to definitely show the rotor also. Here is my rotor. Normally, induction motor will have something called auxiliary winding. We will talk about this within a short while, but this is the auxiliary winding or starter winding which is meant for starting the machine, that will normally have a switch and a capacitor as well. The capacitor is meant for creating some phase shift in the auxiliary winding current, and this is the switch which will be opened once the motor starts. I do not have to have the auxiliary winding eternally in the circuit. Initially only for starting I will need this, later on I can open it out. Now, this is the circuit diagram corresponding to the single phase induction motors no load test. So, this is the main winding. Okay. Now, what I have got is V0, I0 and W0. Under this condition, we are going to assume that the speed is close to synchronous speed, which means S is going to be almost close to 0, but 2 minus S is going to be approximately equal to 2 itself. So, if you actually look at the equivalent circuit once again, very clearly this portion is going to definitely carry, sorry, this is the resistance and this is the inductance. I have just drawn it the other way around, does not matter, but this is essentially going to have the resistance which is R2 dash divided by 2 into 2 minus S, and 2 minus S is after all 2 itself because S is close to 0. So, I am going to have R2 dash by 4 as the quantity here, right. So, this is under starting condition when I am talking about starting no load condition, sorry, no load condition. So, under no load condition I am going to have this to be R2 dash by 4. So, the first thing I need to do is, unless I have the R2 dash value, I cannot say how much is dissipated in among W0, how much is dissipated in the backward revolving magnetic field circuit. So, I have to actually say W0 minus I0 square R2 dash by 4 is what is the no load loss. In fact, I should also subtract I0 square R1 because this is also not a small quantity. I have to subtract both these quantities from W0 to get what is the no load loss, because I0 itself will be a good chunk of the total rated current. I0 will be normally 60 to 70% of rated current. So, I can't completely neglect this or this. That is the reason why we are taking into account. This R1 and R2 will be actually determined only from the short circuit test or block rotor test. I will come back to the other calculation shortly. So, in block rotor test, the speed will be 0. I need not connect, do not connect the auxiliary circuit at all, or do not connect the auxiliary winding circuit. Then automatically if I open the switch, whatever I had shown, if this switch is open, I am going to essentially not allow the machine to start. So, in this particular case also we are going to have essentially the circuit similar. I am going to have the variac here. This is the single phase 230 volts 50 hertz supply. I am going to have an ammeter, I am going to have a wattmeter, and I am going to connect it to the main winding. I do not even care about anything else. Of course, my rotor is here sitting idle, it is not going to rotate. Now, this is the current coil, this is the pressure coil, and I am going to measure the voltage here. Okay. So, what I get here is WSC, VSC and ISC. Under this condition, block rotor condition, because omega m is 0, S is equal to 1. It is essentially omega S minus omega m divided by omega S, which will be equal to 1 anyway. So, 2 minus S is also 1, both of them are 1. So, you can see that the two equivalent circuits can completely be merged. R2 by 2 into 2 minus S will be equal to R2 by 2S itself. So, I can simply draw this as a single equivalent circuit like what we do in the case of a 3-phase induction motor. So, I should be able to say that whatever I get as WSC will be equal to VSC ISC cos phi SC. So, from which I should be able to say what is cos phi SC. Once cos phi SC is determined, VSC by ISC is ZSC. So, ZSC cos phi SC will be R1 plus R2 dash. Similarly, ZSC sin phi SC will be X1 plus X2 dash. I can assume almost both of them are equal to each other. So, I can say ZSC cos phi SC divided by 2 is R1, ZSC cos phi SC divided by 2 is also R2 dash. So, I should be able to get the values directly. Once I get the values of R1, R2 dash, X1, X2 dash, I should be able to actually get what is the no load loss from this expression. So, I can say W naught minus I naught square R2 dash minus I naught square R1 equal to W no load. Once I get the P no load, I can do rest of the things directly. Like I have V naught, so I can say V naught square, right, divided by RC equal to normally W no load. So, I can get what is RC. RC equal to V naught square, V naught square divided by W no load. So, RC once we get, it is a piece of cake to get XM, because I can say V naught by RC equal to IC, from which I can say I naught square minus IC square square root equal to IM, and V naught by IM equal to XM. So, I have got everything. I have got XM, I have got RC, and I have got R1, R2 dash, X1, X2 dash. All of them have been inferred using block rotor test and no load test. Once I have these things, we should be able to calculate all the performance parameters using all these expressions without any difficulty. Okay. Now, the last but not the least, we will look at some of the starting methods of single phase induction motor. Although the load on the single phase induction motor will be small and the machine is also really miniaturized, we need to have some starting methods so that it starts on its own. So, normally if you look at the auxiliary winding, if I say that my main winding is going to have the axis like this, right, this is all dot and this is all cross. So, I am going to have the main winding axis something like this, right, the flux. Auxiliary windings axis will be always at 90 degrees to that. So, I should essentially show, if I show it as a concentrated winding, if I am showing main winding like this, I should show the auxiliary winding as though this is like this. So, this is M, MM, this is A, AA. This is how it will be. They will be at 90 degrees. But what I want is, I want to make this particular machine function like a two-phase induction motor. Two-phase induction motor will normally have two windings. In three-phase induction motor, there will be three different windings which are phase shifted from each other by 120 degrees. Here, there will be two windings shifted from each other by 90 degrees. That is what we have done precisely here. You get my point, these two are shifted from each other by 90 degrees. But we should also have the currents time displaced from each other. By 90 degrees. So, we will normally have to provide maybe a capacitor, which will actually, if I say that if this is going to be my voltage of the induction motor, if I am going to have this as the main winding current which is lagging behind by certain angle, let us say phi m, I would like the auxiliary winding current to exactly be at 90 degrees, if it is possible. So, this should be some IA. If I am able to do this, then these two are actually displaced from each other by 90 degrees, their fluxes will also be displaced from each other by 90 degrees, it will actually result in a revolving magnetic field. So, I have to have this as phi A. If I want this current to be leading, maybe I should put a capacitor, but the capacitor cannot be put inside the slots. That is the reason why we normally what we do is, if this is M and MM like this, I am going to have a capacitor externally connected along with auxiliary winding coming here. Okay. Now, I am going to have the cage rotor sitting here. This is the overall structure of the single phase induction motor along with starting arrangement. So, the starting method, the major concept of the starting method is to displace the current in the auxiliary winding by certain angle as compared to the main winding current, right. So, I have different methods. The first method I would say is resistance starter. So, in this case basically auxiliary winding is going to be highly resistive, whereas main winding is going to be highly inductive, right. This is generally called as split phase starter, because you are essentially trying to split the phase angle between auxiliary winding and main winding. So, I am going to have, if this is the voltage, main winding current is going to be lagging quite a bit. So, this is phi m, whereas I am going to have phi auxiliary lagging behind very slightly. So, this is going to be I auxiliary, this is going to be I main, and I am going to have the phi auxiliary to be really small. So, still there is a good amount of phase angle between these two, which will actually create some amount of revolution as far as the flux is concerned. So, starting will be possible, although it is not exactly 90 degrees, still there are two phase shifted winding and time shifted current. So, it will be able to create some revolving flux. This is one of the methods. Then the second method is generally going to have capacitance start motor, which is very commonly used in our ceiling fans, which I have already explained. So, I am going to have the voltage along this and I am going to have probably the main winding current here, whereas auxiliary winding current I would like to arrange it in such a way that I get a capacitance like this. So, in capacitance start, only during starting the capacitance will be used, after that auxiliary winding will be opened or auxiliary winding switch will be opened, which means this switch will be some speed sensitive switch. The moment the speed reaches maybe 80% or 60% of the normal speed, we are going to essentially make sure that that is opened. So, centrifugal force or something will open it. So, we will call this as a centrifugal switch. So, this is very commonly used in many of the configurations. The third one normally may be capacitor start, capacitor run, motor. So, in which case here if I am going to have actually this as the main winding, and I am going to have through the switch auxiliary winding, I should not show the switch here, rather I should show the switch here along with the capacitor and auxiliary winding. So, this is the auxiliary winding, this is the capacitor which is the starting capacitor, and this is going to be the switch. Apart from this, I am also going to have a running capacitor. So, the running capacitor may be something like 30-40 microfarads if it is a 0.5 HP motor, whereas I am going to have quite a large value, maybe 250-300 microfarad for starting. So, starting capacitor value will be larger, running capacitor value will be smaller, but having the running capacitor will enhance the torque that is coming up in this particular motor. So, this will improve the performance in terms of both torque production and the power factor as well, both, right. So, that way this will be really good. Sometimes we may have only capacitor run motor, that is only one capacitor will be used in series with the auxiliary winding to make sure that it is going to be there in the circuit during running as well as starting. That may not give such a high starting torque like what capacitor start motor gives, but still it is manageable. Okay. The fourth one, which is a shaded pole motor. In shaded pole motor, what happens is, if this is one of the poles, I am going to have a small protrusion in this pole. Similarly, I am going to have a small protrusion in this pole. This is the main winding, this is also the same main winding. Now, what is going to happen is, this protrusion will have a small shading ring which is very thick, it can be a copper ring. So, this will have R to be low, X to be high, whereas this is going to have R is actually also high, but X is not too high, they are comparable, because of which it will look as though the flux here, because the current will be more lagging, the flux induced current will be lagging, flux will be lagging. So, this flux, right, this flux is going to be leading as compared to the flux here. The flux here is lagging, whereas the flux is leading here. So, it will look as though you are going to create a phase shift between these two. So, it is like creating a revolving magnetic field, but here the torque generated will be really low. So, typically in a hair dryer where the torque generated need not be very high, in those cases, or let us say there are toys where there may be a small fountain which is pushing the water up or down, in those cases you may require these kinds of motors. So, toy motors, or we may use this normally in hair dryer. In those cases, we may be using this kind of shaded pole configuration. So, I am not really getting into the details of how to design the starter winding. I am not really getting into this because that will be very much beyond the purview of this course. So, if anybody is interested, they should refer to any special book on single phase motor. So, on the whole, what we had done in this particular lecture was to go through an overview of single phase induction motor. So, we actually looked at, we started off with basic principle of operation of the single phase induction motor after starting with the constructional features. Then we looked at the operating principle based on double field revolving magnetic field theory. Then we looked at the equivalent circuit and how to really determine the equivalent circuit parameters. We looked at open circuit and short circuit test. We also got the expression for the torque and power, and finally we looked at 4 of the starting methods. So, that is all I have to say about the single phase induction motor, and thank you very much for your attention.